Hello, my name is EBehara, and my project discusses and evaluates the role of an object's moment of inertia in regards to its motion. Moment of inertia is defined as the mass of an object and how it is distributed across its rotational axis. An object's moment of inertia depends on the location of its rotational axis, either about its center of mass or elsewhere. The quantity of moment of inertia can be used to calculate a torque needed for a desired angular acceleration. However, it is important to note that an object may be harder to rotate depending on how its mass is distributed. The role of moment of inertia on an object's motion has to do with its rotational kinetic energy. Rotational kinetic energy is the kinetic energy of an object's motion based on its rotational component rather than its tangential component. The equation for rotational kinetic energy is equal to 1/2 times the moment of inertia times the angular velocity squared. Based on the law of conservation of energy, mechanical energy in this project will always be conserved. To account for rotational kinetic energy, the total kinetic energy equation will be the sum of the kinetic energy of the center of mass and the rotational component of kinetic energy. Therefore, the total energy equation will be the sum of the initial kinetic energy of the center of mass, or tangential kinetic energy, the initial rotational component of kinetic energy, and the object's initial potential energy, equal to the final tangential and rotational kinetic energy components and the final potential energy. This equation can be further simplified by plugging in the formulas for each individual quantity and canceling out the initial kinetic energy since the object started rest, as well as the final potential energy, assuming that the bottom of the ramp represents the origin. Simplifying further, we can now cancel out mass and radius squared, leaving us with an equation for each object's final velocity. V final equal to the square root of 2 times g times the height divided by 1 plus c being the constant in each object's moment of inertia, which is dependent on its shape. This final speed will change depending on this constant, because kinetic energy is split into its rotational and tangential components, and c determines how much rotational kinetic energy plays a role in the total energy of this object. In this project, 4 objects will be used to study the role of moment of inertia: a sphere, a hoop, a cylinder, and a frictionless point mass. The equation for moment of inertia follows the general form of I equals a constant based on an object's shape and rotational axis times the object's mass times the radius squared. Each object's respective moment of inertia equations can be seen here. We can assume that the cylinder is modeled as a disk, and we can also assume that these objects are rolling without slipping. In this model, we have 3 objects shown: a sphere, a hollow hoop, and a cylinder. Each object has a constant mass of 1 kilogram, and each ramp has a constant height and an angle of 30 degrees from the ground. For simplifying purposes, all of these surfaces are frictionless, and air resistance, as seen above, is negligible. A common misconception would be to think that all of these objects would reach the ground at the same time and thus have the same velocity due to all of these constants. Let's see what happens. I'm using a slower simulation speed to get a better visual. As we can see, the sphere has the fastest velocity, followed by the cylinder and the hoop. This is because, based on my previous equation, the final velocity is determined by the moment of inertia constant, which is based on the object's shape. What happens if I increase the mass of the sphere to 2 kilograms? As we can see, there should be no change since the final velocity of each object has no determination based on the mass. This should also be the case if I increase the mass on the other 2 objects as well. Now what would happen if I were to introduce friction to the fastest moving object, the sphere? I have given the sphere a coefficient of friction of 1. Assume each object has been brought back to its constant mass. We can now see that the sphere hits the ground later than the cylinder, which is a change from previous experiments. This most likely has to do with the force of friction opposing the motion of the sphere, and in order to keep all forces and total energy constant, the final velocity must decrease. The exact changes for each object will differ based on the other forces such as gravity and normal force acting on each object. Finally, I'm going to model one more object in this race, a frictionless point mass. In here, the point mass will be modeled as a cube. since it should not have any rotational component. Let's see how its final velocity compares to those of the other three objects. As we can see, the final velocity of the cube point mass is faster compared to all the other objects. This is because, as I said earlier, there is no rotational component to the point mass, meaning there is no rotational kinetic energy. Therefore, there is no splitting of the velocity for each energy component, and rather, all the kinetic energy is of the center of mass, is completely translational, and fully transfers to the final potential energy. This will lead to a higher final velocity for the point mass overall. In conclusion, one of the biggest takeaways from this project is that mass does not actually affect the rotational or tangential motion of an object, but rather, when an object is rolling down a surface, it is the properties of its shape that actually determine its final velocity. I found this to be especially surprising since it goes against what one might think and addresses a common misconception in physics. Another physical quantity that will impact the final velocity of an object will be the opposing friction force as it rolls down a surface. Friction force can reduce the overall velocity of the object by acting against its motion due to the overall conservation of forces that is still taking place, despite this not being shown in the original equation. I also learned that the reason why the point mass will have the highest final velocity is due to it not having a rotational kinetic energy component. Therefore, all of the kinetic energy of the point mass will be the kinetic energy of its center of mass and will all transfer to its potential energy rather than being split. Also, the point mass was completely frictionless. Another thing I learned was that the increasing moment of inertia constant can decrease that object's velocity, since an object with a larger moment of inertia is harder to put into motion. More energy is required to rotate this object about its center of mass, and less excess energy is available for the motion of the center of mass, or the translational kinetic energy. This assumes that potential energy will stay the same in order to conserve total mechanical energy. Based on this, the lower moment of inertia will lead to a higher velocity as seen with the sphere. Some simplifying assumptions made in this project are that air resistance is negligible, each object rolls without slipping, there is initially no friction between each surface and its object, and total mechanical energy is conserved. Some things to note about the modeling of real-life situations. One positive outcome was that the model could portray when total mechanical energy was conserved, as well as when the surface was frictionless and air resistance was negligible. These worked out when using my simplifying assumptions. However, in real-life situations, air resistance being negligible is not always accurate. But since we in Physics 191 have not modeled a problem using air resistance, it was best to make that quantity negligible for this project, even for the sake of reducing real-life accuracy. Another limitation with this model is that the material used being the default material. Since this material is not identifiable in real-life situations, it is hard to use the coefficient of friction given and take it as accurate, which is why I started this project by assuming all surfaces were frictionless. The frictionless surface used for the point mass was the ice material, which in real life still has a minimal friction that had to be adjusted in this model, since in real life it is challenging to find a truly frictionless surface naturally. A final limitation with my model is the modeling of the movement of the point mass. A point mass is defined to be a particle with no shape or dimensions, and also no rotational component. In order to accommodate for the lack of rotational kinetic energy, I modeled the point mass as a cube. However, a cube is still an object with dimensions and shape, meaning it is not a completely accurate point mass model. In addition, there was no exact cylinder model or tool in Algodoo that was available, which led me to using the circle tool and making certain geometric adjustments in order to model it as a cylinder. However, this could also hold its own inaccuracies due to the shape not being exact. Thank you so much for watching.